So hello everyone, welcome you all to this new video. So till now we have covered all the modules of VLSI design and testing, right? So we have one more subject in your syllabus of 6M EC, that is I thought to cover this because since the lab exams are approaching very near, so that's why I thought that people would be needing it, so I thought to do it. So there is one more subject called as VLSI Design and Testing Lab, right? So here the concepts related to VLSI which we studied in theory, some of that would be applied to the laboratory experiments as well. So these experiments are listed as below. Okay, so this course code is BECL 606. Again, it has the CI marks of 50. I hope that all of you might have been given it. Next, we have semester and evaluation also. That is also out of 50. That is the final exam. So this credit, one credit subject and 3 hours exam. Okay. So these are the list of experiments here. Okay. So there are around 12 experiments, and I'm going to try to cover around 7 to 8 experiments for you guys. Okay, which are very important ones. Okay. So in this syllabus, the first experiment is designing a 4-bit adder, right? You should be writing a Verilog description, verify the functionality using test bench, synthesize the design by setting proper constraints, and generate the gate level netlist. Okay, so this is the first experiment for you guys, that is designing of 4-bit adder. So in this video, I'm going to do this experiment for you guys. So I'm going to do this using the software called as Vivado. Okay, so I don't know whether you guys have heard it or not, whether in your college this software is being used or any other software is being used, because this software is very essential for a VLSI based circuits. Okay, so that's why I thought of doing this. It's a very costly because our college has provided using this amount of lakhs and lakhs of money. So this is very expensive, and its storage is around 100 GB. Okay, you should having a 100 GB free space in order to download this Vivado software. Okay, so this is very essential, but the software is very good. Okay, I've already tested it. So some of the experiments we are going to do it in Vivado software, which is associated with Xilinx. Okay, then some of the experiments that is related to the CMOS circuit implementation of inverters, expression, two input NAND gate, NOR gate, everything and all. Those things we are going to do using the electric launcher. Okay, where we are going to do the schematics as well as the layouts. Okay, yeah. So that was about the introduction part of briefly about the syllabus. So this is the first experiment. So let's see. Before that, let us see the code. Okay, for 4-bit adder. First is for 4-bit adder, right? So this is the 4-bit adder. So first we should be they have mentioned to write the Verilog description. So we should be writing the Verilog code. After that we should be writing the test bench code. So what I'm doing is I'm just explaining the code first about how the 4-bit adder works. And after explaining the code, I would be opening that software and I'm going to copy paste that code. Okay. Then I'm going to tell you the complete procedure of Vivado. Okay, how to put the code, Verilog code, test bench code, and how to check for the simulation and how the output waveform is going to be obtained. Okay, everything I'm going to tell you. First is 4-bit adder. So first, we should be declaring the module name. So some of you in the third sem, you had I guess a Verilog subject. Okay, in that you might be knowing how to declare the modules and all in the Verilog code. Module. Then after that, you should be giving a module name. Adder. I've given it as adder. You could be giving any name. It's up to you, but you should be remembering that. Okay. Module adder. Then declare the inputs and outputs. That is here in this case, A, B, C in are the inputs. Sum and carry are the outputs. Okay. So before that, I'm going to tell you. I guess most of you might be knowing it, how the 4-bit adder or the 4-bit ripple carry adder works. Okay, so it would be having 4 blocks, that is 4 set of full adders. Okay, then in the one full adder you would be having 3 inputs, that is A naught, B naught, C in, that is carry input is given. Then we are having sum and carry out. So the carry out of the first adder block, that is fetched back as the input of the second adder block. Okay, so for example, if we have the inputs as A naught, B naught, and C naught in the first adder block, and the output is sum and carry, that sum naught, S naught, and carry C naught is, that carry is given to the input. That same carry is given as the input to the next adder block. Okay, so like that the sequence goes, and it goes up to the 4 blocks of 4 full adders. So I hope this you might be knowing it, but still I thought to tell you. So the working and all I'm going to explain you while I get the output waveform. Okay. Input, I've declared it as input 3 down to 0 a comma b. Why 3 down to 0? 3 down to 0 indicates that they are 4 bits. Okay, so the inputs are of 4 bits, a and b. So that's why 3 down to 0 a b. And input carry in, carry input is always 1, that is either 0 or 1. The carry produced is 0 or 1, that is a single bit. So that's why it is seen. Output 3 down to 0 sum, the sum produced is again 3 bits, 4 bits. Okay, output is carry. Then wire 3 down to 1 W. This wire is indicate that it corrected 3 down to 0 to include the W of 0. Okay, which needed in the full adder one. So that's why it's mentioned as 3 down to 1. So as I've told you, we are using 4 full adders. So they are named here full adder FA0, FA1, FA2, and FA3. In the first full adder, the inputs are A of A0, B of B0, C in, sum and carry of W1. Okay. Then, as I've told you, this carry of W1 is given to the next full adders as the input. So that's why here the next full adder inputs are A of A1, B of B1, and C in. This carry out, right? That is given as the carry in of W1. Okay, you see here carry in of W1, then sum is sum of sum 1 and carry of W2. Now this W2 is given to the next full adder as input here, you could see here. Okay, A of A2, B of B2, C in of W2, sum of 2, carry of W3. So now this W3 is given as the input for the next full adder again, C in of W3, sum of sum 3 and carry of carry. So this carry of carry indicates the final carry output, okay, after all the 4 full adders are given. So this first full adder is having the carry input here. Okay, this is the carry input, and this is the fourth full adder which has the carry output. Okay, then after declaring this full adder, this is just the declaration part about how the 4-bit adder works. In that way I've written this in the how the block diagram, I've written this in form of a code. Okay, then we have end module to end the module. Okay, then after that declare, we have declared for full adder, right? But we have not declared how the full adder works. Okay, so the full adder works you should be declaring about. You know that full adder is again having 3 bits, 3 inputs, that is a b c in some carry. So first declare module full adder, sum carry are outputs, then inputs are a b c in, output is sum and carry. Then sum, what is the expression for sum and carry in case of full adder? I hope you might be knowing it. Sum is given as assign sum is equal to a XOR b XOR c in, and assign carry, that is a b. This straight line indicates plus bc in, that is and a is anded with b. So these two are taking in and operation, these three. Then the middle line indicates that they are getting added up. Okay, so sum and carry expression, you write it, then end the module, and like this the complete Verilog description code for 4-bit adder would be completed. Now write the test bench code. This test bench code is used in the to get our output waveform. Okay, this is everything. This part is the initialization part. Okay, whatever we have understood from the circuit, we should be writing in the Verilog code in the form of a machine language code. You should be writing it. Then the test bench code, again while writing the test bench code, what you should be doing is module adder 4-bit test bench. Okay, give one any one name is again it's left to you what name is given. Okay, you could be giving any names. Adder 4-bit test bench I've given. Then register. Now in order to represent in the test bench inputs and outputs, inputs are named as reg and outputs are named as wire. Okay, so here the inputs are a b c in. A and b are 4 bits, then c in is a single bit. The output sum is 4 bits, carry is again single bit. Now adder u of adder. Okay, then declare all the variables, that is a b c in, sum and carry. Then initial begin a equal to 4 dash b 1111, b equal to 4 dash b 0001. Any two values you give, c in value, and this is the monitor, that is this would be shown in the display of the output, that is a equal to percentage b. So this b is any variable that shows the number. This b stands for binary. Okay, either 0 or 1. Okay, everywhere this b stands for binary. A b c in some carry. For all these the binary value you would be getting as the answer in all these input into all these bit values. Okay, so like this end the code, and finally you write end module at the end to declare the end of the test bench. So this is the complete code, guys. So now this code, what I'm doing is I'm going to execute in the Vivado software. Now let us go to that software. So this is that software, Vivado. Okay, what I was telling about. So with this software, easily we could be doing the simulation part of the circuit, where we should be dumping the Verilog code as well as test bench code in a particular window. That step-by-step procedure I'm going to tell you now how to do. It's very easy, guys. Just follow what and all I'm doing. Okay. First thing is should be any in order to create any circuit, right? We first go for create project. Okay, this open project indicates that there are some recent projects which you have already done. If you want to edit that, you should be clicking on open project. Okay, yeah. So this tasks and learning centers and all are not required here. Create project option is there. Go click on that. So it would be taking some time. So this window would be appearing. Go to next. Okay, so now you give any project name of your choice and set one location where that project would be saved. Okay, so you could be setting any location, it is up to you. Okay, project location, you could be clicking on these three dots and set whichever location is required for you guys. Okay, now project name. So here what I'm doing is I'm going to give the project name as FA, that is full adder. Okay, click on next. So the FA is already there. So what I'm doing is I'll give full adder. Okay, so after that, this window would be appearing. This RTL project and this tick mark should be there. Rest all things you keep it as it is. Then go on next. Okay, after that, this window would be opening. So here we have two options: parts and boards. Okay, you should be selecting boards here. Okay, after selecting boards, some boards would be appearing here. Okay, we should be selecting any of the board. Okay, it's of your choice. Okay, select any board. I'm selecting this first board. Select it and click on next. Now finish it. The summary part is done. Now the project would be getting initialized and one window would be getting opening. Okay, so see here. So now here, now here the code part comes, that is we should be dumping our Verilog code as well as test bench code. For that, how to where to dump, you should be seeing here. That is there is one in the top left, we have in the project manager bar toolbar, we have here one option called as add sources. Okay, see I'm showing here add sources. Click on that. So for first we should be doing for Verilog code. So for Verilog code, there are three options here. We should be selecting the second option, that is add or create design sources. Okay, then click on next. Then here there is one option called as create file. Click on that. Now give one file name of your choice. So what I'm giving is I'm giving full adder. Okay, so now that file is created here. Okay, now click on finish. So here this also you click on OK. So this is in the code only directly. You could be declaring the how many bits inputs and all. That's not required. That is in the code. When I explained that, I already included it. So this is not required. So click on OK. So yes. So now that window is getting created. Okay. So it's getting updated. Now you should be checking for that window. So you see we have created the full adder, right? So click on that full adder. Okay, so this window would be getting opened here. In that we should be putting our complete Verilog code. Okay, so first I'm deleting these stuffs. So here that code which I've already told you, right, that I've already copied and kept it here, that I'm going to paste it here right now. This code I've already explained you, right? So this is the complete Verilog code. Now see here, this is the complete Verilog code which I've explained. I've dumped it here. Okay. Now you see here in the top right, there is one green light, right? That indicates that the code is error free. Okay. There is no errors in the code. Okay. So if the code has some errors, right, this would be showing as red here. So see, for example, I'll do one mistake here. The bracket I'm removing here. Now see here, this would be turning red here. Okay. Because after removing the bracket, the complete this would be won't be 4 bits. So that's why the errors are showing here. So you could see the red light, right? So red color that indicates that there are errors in the code. So where and all there are errors in the code, there the lines would be appearing here, that you should be clicking, and in that line the code would be having the errors. Okay, so now again I'm doing here, I'm closing that square bracket here right now. Now see, again the light would be turning to green. So now the code is error free. After that, click on save. Okay, so here this in this source window, you could see the code is getting updated. Okay, so now that code is updated, Verilog code is done. Now next part is the test bench code. Test bench code, again the same thing, same procedure. In the project manager toolbar, go to add sources. Now in order to execute the test bench code, you should be selecting the third option, that is add or create simulation sources. Okay, next, again create file. Now you give the name as full adder underscore tb. Tb means test bench. Okay, so this file is created, finish. Okay, yes. So now that it is getting created in the source window, now go to simulation sources. So here, see here, we have one file name called as full adder. You should be searching for that file name which you have given, that is full adder underscore tb. Click on that. So this window would be getting opened. Here we should be typing our test bench code. So that also I have already copied and kept it here. So see here, again there is no errors in this code because there is a green color indicates that there are no errors. So in the test bench code, one thing you need to be remembering is, okay, when you, if you want to link the Verilog code and the test bench code together, in the test bench code there is one here in the seventh line you can see we have written adder u underscore adder. Okay, so this adder indicates that indicates this adder which you have declared, that is the module name which you have given for this Verilog code adder. This, the same name should be given here to the test bench code, so that that Verilog code would be getting linked to this test bench code. Okay, so that is part, that part is done here. Now there is, this code is error free. Save it. So now it's getting updated. So it is updated now. Now final thing is go for run simulation. You should, in order to check the waveform. So here in the simulation window, simulation, you see here there is option called as run simulation. Click on that. Run behavioral simulation. Now the simulation is getting executed, and we would be getting the output window. See here, the window is opened. So just full this window. So this is in the range of picoseconds. So if you want to make it in the range of nanoseconds in order to see the waveform correctly, click on this uh, under fit, zoom fit. So click on that. So now the complete plot would be in the nanoseconds. So see here, this is the input A, B, C in, sum and carry. C in and carry are 1 bits, and A, B and sum are 4 bits, that is 3 down to 0. Okay, so this is 4-bit adder, right? Now you see here, the value of A is now F. Okay, that is how to represent F in binary, that is 1 1 1 1, right? So that so see here, all the signals are 1 here. Okay, then the value of B is 1. Okay, so value of B is 1. So how 1 is represented in binary, that is 0 0 0 1. So like that only we have 0 0 0 1 here. Carry in is 1. Okay, so sum. So now what you're doing is, the 3 bits would be getting added here, that is 1 1 1 1 plus 0 0 0 1 plus the carry is 1. Okay, now the sum, our answer, we will be getting it as 1 1 1 1 is how much actually in decimal, it is 15, right? 15, then plus 1, then carry is also 1. So the answer we will be getting it as 15 plus 1 plus 1, that is 17, right? But here 17, if you want to represent it in binary, we should be representing it in 5 bits, right? Because in binary till 15 only the 4-bit is possible. So that's why one carry would be definitely generated. So now see here, 15 is 1111, right? So 16 would be 10000, right? 17 would be 10001. So that only you see here in the sum. Okay, in the sum we have the value as 1 here, and the answer is 0001, and the carry produced is 1 here. Okay, so this indicates that the carry 1 is produced, and the answer is 10001, that is 17. Okay, so since it is a 5-bit number, so one carry would be getting produced. Apart from that carry, our final sum would be 1, that is 0001. So the same answer we have got here. Okay, you could be checking for different other values as well. Okay, so this is the this full 4-bit adder gets satisfied, and this proves to be correct. Okay, so that's all, guys. This was about one simple simulation about 4-bit adder. I hope you understood something from this. So in the upcoming videos, we are going to discuss with much more experiments, okay, related to multiplier, 32-bit ALU, flip flops, and other stuff. Okay. So that's all for this video, guys. Like, share, subscribe to our channel. Keep supporting us. Thank you.